Wah-wah? What is this? How does it work? I'm Professor Fiore, and we're going to dive into this right now. Hey folks, it's time for us to examine the wah-wah pedal, a very popular effect for electronic musical instruments. Typically people think in terms of guitars, but wah-wah pedals can be used for other instruments. Bass guitar, keyboards, you name it. You could use it on your voice if you're a vocalist. But, very often when you say wah-wah pedal, people sort of immediately think in terms of a guitar. Now, one of the things I really like about the wah-wah pedal is the name. Wah-wah. It's a wah-wah pedal. That's, the name of the thing sort of reflects the sound that it actually makes, right? We have a term for that. It's automatopoeic. So there are certain words, like zoom, okay? They sort of echo the sound that you're trying to name, right? So the sound that a wah-wah pedal makes sort of makes this wah, wah, wah kind of sound, all right? Technically, it's a fairly straightforward circuit. It's a bandpass filter of reasonably high Q, maybe around 10. Varies a little bit, but we'll just use that as a figure of merit. We simply take the resonant frequency and we sweep it up and down in the spectrum as you're playing. And that's controlled by a foot pedal, right? So you press your foot down, you put your heel back, whichever, and that shifts the resonant frequency, and then we get this wah-wah kind of sound, all right? It's possible, and I'm going to show you this, that you can also control this with an LFO, a low-frequency oscillator. But again, the typical unit that you would buy, and I'm thinking in terms of maybe a Dunlop Crybaby, which is sort of, the marquee kind of thing, long history. It's just foot pedal control, and that's it. All right. Now, one thing to note about the Q of the filter that we're using is it's not a constant Q. A lot of the active filters that we've looked at are constant Q circuits. In other words, you change the resonant frequency. If the Q was 10, it's still going to be 10, right? You change it from 1 kilohertz to 500 hertz to 3 kilohertz, whatever it is, the Q is the Q is the Q. That's not necessarily the case in some of these designs. For example, in the Dunlop Crybaby, the Q is a little lower at high frequencies than it is at low frequencies, right? So it's like an inverse relationship with frequency. You might like that effect sonically, you might not. The one we're going to look at is constant Q, right? Although, unlike typical pedal, the Q on our design is controllable. So you can dial in the sort of effect that you want that way. Now, the old style pedals that I'm thinking of, typically these were made with just RLC circuits, passive resistor, inductor, capacitor circuit that was sort of subsumed inside a transistor stage or two to sort of support that. There are other ways you can do this. You can use active filters, active resonant filter, so that way you don't have to use an inductor. We generally don't like inductors because they're not really well behaved. You can also use a state variable filter. That's the approach I'm going to show you here. That allows us to do some really cool voltage control stuff. You could also use a biquad filter. That's kind of an interesting choice if you want to play around with that, because the biquad also has this changing Q, but it actually changes in the opposite direction that you would see in the old style wah-wah pedals, so that the Q actually increases as you go up in frequency rather than decreases. Okay? All right, so the design we're going to look at is based on a voltage-controlled state variable filter. And this will give us a lot of latitude to kind of monkey with things. Among other things, we're going to see that we have an extended resonant frequency sweep range, so we can get much wider range of resonant frequency. We're also going to have adjustable Q and the possibility, if you're so inclined, of throwing in a low frequency oscillator. So you can have this thing automatically cycle and do its wah-wah on its own. Kind of like a tremolo. You know, you turn on a tremolo pedal, right, a stomp box, and it just does its thing, okay? And you could kind of do the same thing with this, instead of being controlled by the instrumentalist. Your choice. So let's take a look at the curves that you would see on a typical wah-wah. So this is the Crybaby that I mentioned earlier. You search around the net, you can find curves like this. So this is a set from the extremes of position on the foot pedal. So here we have the highest resonant frequency, here we have the lowest. And just by looking at this, you can see the change in the Q, right? This Q is much lower, it's a much broader curve than down here at these lower frequencies, right? Note that the gain over here is 20 dB, so some of these, especially these lower frequency ones, you are just exceeding about 20 dB of gain. So in other words, a factor of 10 in voltage gain, okay? Now, as we go up, there is a little bit of a decrease in the amplitude, but that's not like a huge thing. That's just a few dB. But, you know, the overall volume change is sort of compensated because you have a somewhat wider bandwidth over here. All right. If you try to measure these, this is around at the low end, maybe 400, 450 hertz. It's kind of hard to tell with the scale, but I'm going to estimate that's probably somewhere around 450 hertz. On the top end, this is stopping at about 2 kilohertz. It's also important to note that if you look out here, where these curves are continuing off the resonant peak, this is a first order system. This makes perfect sense. In other words, this is falling at 6 dB per octave or 20 dB per decade, which with a simple resonant RLC circuit, that's exactly what you would see. First order roll off on the bottom, first order roll off on the top. Okay, so let's go and take a look at our circuit. Wow, look at all these things. First thing I want to say is, integrated circuit-wise, this is not nearly as complicated as it at first looks. So I want to point out op-amp, 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 op-amp. There's 4 op-amps here, and I'm using a TL071, which is a standard, you know, stock sort of BiFET op-amp, nice op-amp. You can get a quad version of this called the TL074. So it has 4 071s in one package. So this, and this would be one package. Then I have 2 OTAs over here. All right, so that's an LM13700, which is itself a dual. So that's the second package, right? And then, of course, you have a bunch of resistors and pots and, you know, caps and things like that. But it's really not nearly as component intensive, if you're going to make a board, you know, PC board, as it at first looks. All right. Okay, so if you've seen the prior videos, the ones in the playlist, in the op amps playlist, they come right before this on the state variable filter, and especially like the parametric equalizer, where we're talking about you know, variations on the theme. Voltage controlled filter is another one. You know, we use these OTAs here to get us the voltage control. I mean, you can do manual control, but the whole point of this is to look at something that's sort of, I don't know if this is a word, automatable, okay? So that we can do some cool stuff with it. But basically, you know, the state variable filter is comprised of this input summing amplifier, this second op amp here, which is an integrator, and the third one, which is also an integrator. So this is a 3 op amp version of the state variable filter. There's also a 4 op amp version, but we don't really need that for this case. All right, so the controls that we have. The first thing is, you will notice I have a high input impedance buffer over here. There's a 1 meg. This is just a DC return, DC bias return. So this gives us a 1 meg input impedance. So, we have something like a guitar with a passive pickup. This is going to work great. This has a gain of 2, 10K over 10K, just in case you need a little bit of signal increase. And then this just goes through a pot. So this would be your gain pot or your volume pot out here. Then we run into the filter. So the OTAs are in the position of the input resistance on the integrator, and we're basically going to use this to take the input voltage and turn it into a current, which feeds ultimately these integration capacitors. And that's what's going to set the resonant frequency for us. All right. There is feedback through the bandpass output, and this pot right here is going to set the Q of our filter. So I have a pot in here, right? We'll be able to sweep this up and down and change the Q. So right now I have this at 25%, and this is going to give us a Q of maybe around 10 or so. Well, let me put it this way. It'll be comparable to something like the Crybaby. And I'm going to do some comparative curves, and you'll be able to see this. The 10K is here just to limit so that if you dial this all the way out, you don't end up with 0 ohms over here, right? So that sets the limit on what the Q can be. In any case, the control voltage, right, for the two OTAs comes back here. And to keep it simple, you would just have a pot here that would run between the positive power supply and the negative power supply. But that range might be too much. So because it is voltage control, we're going to have a wider range than what you would get on those old RLC type pedals. So I've also included these little rheostats over here so that you can tweak what the farthest frequencies are. In other words, how far up we want to go, right? So this pot will set that. Where does the sweep end? And then how far down we want to go. So that's the P lower is going to set that. All right. This right here, this pot in the middle is the foot pedal. There's a potentiometer that's going to be attached to the foot pedal, right? So as you go up and down, the wiper arm is going up and down with your foot, right? And then I have, which I'll get to in just a sec, an optional LFO switch over here. So you can go back and forth between this foot pedal and this low frequency oscillator. All right. So the first thing I want to do is just do like a Bode plot so we can see what the ranges are. Now I've already sort of walked through this, so you can take a note. If you put the two rheostats over here, the upper and lower limits, if you stick these at 20%, which is what I think I have them at right now, yes I do, then you're going to get a resonant frequency range of about 400 hertz to 2.1 kilohertz. In other words, pretty close to what we have over here, right? Like I said, this was like 400, 450, something like that. This is about 2 kilohertz. So this setting, okay, for these two will get you a similar result. Now, you have an option here. You can use two separate pots to have independently adjustable upper and lower limits, or you can use a dual gang pot, a single dual gang pot, in which case you could think of that as adjusting the width from wide to narrow. That's the other way of doing it, right? By having independent ones, you can have, both of them at the same extreme. In other words, low, low, right? Low frequency, low frequency. But then you could do the opposite. You could do some kind of weird things here, right? Have one in the middle, have one at the extreme top end, have the other, or have it at an extreme low end. You can sort of play with the ranges. But in any case, when these are set up for 20%, you're going to get that same, roughly that same range. In other words, as the wah-wah pedal goes up and down, that wiper arm goes up and down, you're going to get pretty much that same range as the Crybaby had, 400 to 2.1K. If you bring these down to 0%, you get this sort of super wide range. You get over an octave of extension in the bass that goes down to 160 hertz. And then we pick up some on the top end at 2.6 kilohertz. If you go the other way and you crank these out to 100%, then this narrows everything down. And now your bottom end only goes to about 650 hertz, and the top end stops at about 1.4 kilohertz, right? So that's a more narrow range. So you have those kinds of options. If you really want to shift the entire thing up or down, you can change the IABC programming resistor, RABC, So if you set this from the given 27K to a 22K, that will increase the control current, which will shift all of the frequencies up. Okay. And if you made it a little, the other way, if you went the other way with it, it'll shift everything down a little bit. All right. You don't want to do like huge changes here, because then these things will, who knows? These things might go out of the sonic range, right? Range of human hearing. That wouldn't be too useful. But in any case, we can kind of come in here and see what's what. All right. So let's see. What do I have this set up? So right now that's in the middle. So I want to do like a Bodhi plot here. Let's see what we get. Okay, so that's looking pretty good, right? You can see there's 0 dB. This is peaking up nearly 20 dB, and then it's rolling off. And if we measure these out, this will be about 6 dB per octave. Okay. Now you could go back and compare that to the Dunlop over here. Now the only thing I have to do is I have to change the scaling over here. This is going from like 30 to -40. So let's change that. So the upper, we'll make that 30. And then we'll make this -40. Okay. Because otherwise, we're not going to be comparing these things scaled equivalently. And now let's see, let's get our frequency. So there's 100. Let's see, 10K is over thereabouts. So let's bring this guy in a little bit. All right, so now the scalings are about right. Excuse me. All right, so you can see, this is at 1 kilohertz. That looks pretty similar to what we see over here around 1 kilohertz. This Q might be a little higher than what we're seeing over here in this range. It'll wind up definitely being higher up here, but it'll actually be probably lower once we get down here. All right. But my point here is really that this is the kind of curve. If we look at the roll off here, we're getting like pretty much the same slope. All right. Everything looks pretty good as far as this is concerned. All right. Now, just to kind of prove the point here, I go into the wah-wah pedal, put your foot down. Let's turn that up to 100%, and we'll redo this. Lock. All right. Compare that back. Oh, that's right. I forgot to change these. Oh, whatever. The important thing is you can see that this peak has changed, right? This is sitting a little over 2 kilohertz, maybe 2.1 kilohertz, versus over here we have maybe, I don't know, 1.2 or something. All right. So that shows that. That shows that effect. Now we can come in and go the other way. Let's make that like 0. Block. Okay, and you can see that thing dropping down, right? So there's 100, 200, 300, 400. So that's a pretty nice shift, right? We got a pretty nice shift. All right, great. And like I said, that's with these limit pots sitting at around 20%. So if we monkey with those, then we can change what those limits are. Let me bring this back to where we started, 50 hertz. Okay, excuse me, 50%. All right. So that would be the basic operation of this thing, right? You just take your output over here, play your guitar, your bass, whatever the heck it is, have fun with your foot, and off you go. But I did mention at the outset that this is amenable to using an LFO. So I have a little switch over here to go back and forth between an LFO, a low frequency oscillator, and the pedal. All right. Now, if you're wondering why I didn't include this, it's because you can't do a Bodhi plot if you have multiple inputs. That gets kind of confusing. Like, what am I doing? Because actually, as this is changing, the Bodhi plot is changing. And there's no way of sort of animating the simulation in that regard. All right. So you can't do that. Instead, what I'm going to do is I am going to throw in, let's see, I've got the ground already. So let me grab the oscillator here. I'm going to wire this in. And I'm going to change the name of this to LFO, because that's what it is. And then I'm going to change the wave shape. I'm going to turn this into a sine wave. And we're running this on plus and minus 9 volts. So I don't want to use the entire thing. I'm just going to use 5 volts. But this has to be, fairly low frequency. So, maybe like 2 hertz. So it's going to sweep up and down twice in a second. So this will be obvious for us to hear. Okay. And I'm just going to switch my pedal down. Okay. Now the input I'm using is a 100 millivolt peak sine wave. It's the A above middle C, 440 hertz. And I'm using a square wave here because I want some harmonics, right? So this would be like a distorted guitar, subtly distorted guitar kind of thing. So you can kind of hear as the filter goes up and down the way in which it's going to affect those harmonics. All right. Now, like I said, we can't do an AC analysis, but we can do a transient analysis. So we only need to see a few seconds of this. All right. So this is going to be, I'm going to go from 0 to 4 seconds. And when you start doing big, long time simulations, obviously the simulator is going to take a little bit longer. All right. So you have complicated waveforms, bigger circuits, longer output simulations. All those things are going to require more computational power. And the end result is you sit around a little bit more. All right. Yeah, you can buy a faster computer, but, whatever. All right. I mean, this is not taking like a crazy long amount of time compared to you sitting down and actually breadboarding this thing. Okay. All right. There we go. Let us separate out the curves. I mean, we have a pretty good idea what we have here, right? So there's the LFO. This is the input signal, which again, because of the magnification, because this is 4 seconds, this all just blurs together, but in fact, there is the appropriate waveform in here. And here's the output. Okay. So you can see that there's a little variation going on in here as that sweep is going up and down, as the filter center frequency goes up and down, right? Some frequencies are being boosted, some are being cut, all depending on where you are in time. You can see how this sort of links up with the peaks and valleys in the control signal. But let's just listen to the input waveform. Okay, so that's our sine wave at 440 hertz. Excuse me, I said sine, I meant square wave at 440 hertz. All right, kind of static, just sitting there, just a buzz, beep kind of a thing. Now we'll take a look at our wah-wah controlled output. So you can just imagine someone having their foot on the pedal and they're going back and forth at 2 times per second. All right. So you really kind of hear that wow, 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 wow kind of effect, right? Where the name comes from. All right. So like I said, we can have all kinds of fun with this. If you want to get really crazy, you could, through judicious use of some analog switches, you could flick over, have the wah-wah potentiometer control what the LFO is doing. All right. So in other words, you'd have a little switch that would say pedal or LFO, normal operation, LFO operation. And then when you flick on the LFO operation, the pedal would now control the frequency of the LFO. That could be pretty funky, right? Like I said, it will take a little bit of thought as far as getting the analog switches to work on this thing, but it is certainly doable. As I said at the outset, most wah-wah pedals don't even have an LFO, so this right here is like a whole another thing, right? It's a whole separate thing. You'd probably also want to include a bypass switch, right? A hardware bypass, so that you can have this thing set up where you want it, and then you can just hit the on-off sort of button, if you will, bypass switch. and get your clean sound versus your wah-wah sound, right? Because there is no position of the wah-wah pedal where you get the original, right? It's not like maybe a distortion box where you could turn down the distortion, right? You on circuits like that, you want a bypass, so you have like, you know, the clean version versus the affected version. Okay, so that's another thing you might want to add to this. But here you go. Only takes 2 ICs, like lots of integrated circuits, but really, you know, you've got 4, count them, 4 op amps in one package, and then 2 OTAs again in a second package, a bunch of resistors, a few caps, and quite a few pots. And again, I'll repeat, if you want to, this could be a dual gang pot, right? That's entirely up to you. How you want to do the LFO, that's entirely up to you. You know, there are lots of circuits you could use to create maybe a triangle wave. You might want to get fancy with this and have something that does sawtooth, you know, ramp up, ramp down kind of stuff. Just gives you more creative flexibility. I hope you've enjoyed this, and this is Professor Fiore saying until next time, take care and have a good one.